We started with our second algorithm. So the two algorithms we're seeing today, again, keep in mind the worst time algorithm, the worst runtime for those two algorithms is quadratic or big O of n squared, okay? Second algorithm we'll be looking at today is insertion sort. Insertion sort is slightly better. Insertion sort is slightly better than bubble sort, right? There's documentation that even states that Apple uses insertion sort in its own sorting algorithm if the array is a smaller array, right? So insertion sort with a partially sorted array would have a good runtime, right? Insertion sort is also in place like our bubble sort algorithm. But as we see, as we actually go ahead and write down or calculate the insertion sort algorithm in pseudocode, we'll see that it's slightly better in the way that it approaches the sorting part of the algorithm, right? So if we have an unsorted array or list, well, let's not start with this number. Let's start with, say, 80 minus 9. 11. Okay, so here we have an unsorted list. How does insertion sort work? Again, let's go over to a video to see what it looks like. Again, if you come across videos, always share. You could also share the videos that you have. There's many videos on how those sorting algorithms work. There's even some that's actually very funny. So here we have insertion sort. And where's my video? Right here. So here it starts off with the first value, 7. It looks at 8. It looks at the left value. It takes 5 until 5 is sorted. Let me pause this at this point here. So it takes the value, for example, next if it looks at 2, it's going to take 2 all the way left. So at the end of the day, that half of that array will be sorted, right? So it takes 2. Think of it like you're playing cards and you want to sort your cards in your hand. Right? You would take a card, you'd move it all the way to the left. This is exactly what the insertion sort does. So it takes the 2, it will take it all the way to the left of 5. Let's continue. You clapping here? Looking with the hands. Okay, so we see how the insertion sort algorithm is slightly faster given if the array is partially sorted. If it's partially sorted, it does that one pass and it's done, right? As opposed to looking at every element, it would look at, for example, if it's partially sorted and it moves one element, it moves that element and it's done. Yes, sir? Yes, it checks the left side of itself. So the left side is always sorted. It starts off with one element, which is sorted. If you start with one element, it's sorted, correct? Which is that first element. Goes to the second element, checks the left element, that's sorted. Third element, sorts that. So the left side of any element is always sorted. Does that make sense? Yeah, very good. Yes?
So you say like it's slightly better than like bubble sort with the space complexity the
worst case is the same.
Worst case is the same.
Yeah, always look at the worst case.
But better runtime is better comparison to bubble sort.
Given a partially sorted array.
So when you say slightly better, based on what?
Based on the array being sorted, like partially sorted. If both arrays are partially sorted, insertion sort will be the winner there. Okay? But at the end of the day, we're always looking at the worst runtime. And the worst runtime in that case is quadratic.
The same?
Yes. Okay?
So would insertion sort also be worse, or it's better than bubble sort?
It's better. It's better. Exactly. Exactly.
Because it's doing what bubble sort is doing, but simultaneously, like at the same time. It's instead of going
Different approaches. Different approaches. Where bubble sort goes to that entire array.
But this one is just taking number by number.
That in my insertion sort example, if I look at the second value, right? I'm going through my array. I look at the second value, and that's sorted already. I'm done.
Okay.
Right? As opposed to bubble sort. Okay? All right, let's make some examples and we will stop. We'll go into code. So here we have our insertion sort. Here we say 80. 80 is already sorted, correct? Yeah. Based on our algorithm. We look at 9. Minus 9. Is minus 9 less than 80? Yes. Yes. Okay, so let's just go ahead and set that up. So minus 9, 80, 11, 2. Okay. So at this point, this is sorted, correct? Right? The left side is sorted. Next, we look at 11. Is 11 less than 80? Yes. So we take 11, and again, imagine you have a deck of cards in your hand, or not a deck of cards in your hand. You have a deck of cards. Imagine you have some cards in your hand, and you want to sort them. So at that point, you have 11. You want to move 11 left in its current position. Yes?
So this is two different collections?
Yes. Think of them like two different collections there. Same collection, but our position, our marker currently is at 11, and anything left of it is sorted already. But 11 needs to put itself in the correct position in that left side of that array.
I'm sure it'll get clearer once we actually code it, but is it two physically different arrays?
No, it's one. We're just using a position marker, or very similar to like a J variable, to walk through it. So currently our current variable, or we could call it current, is at 11.
Okay.
Okay? Awesome.
There is an implementation though, right? Where you can make a copy and then just use, well, not a copy, but another array and then store the.
If you could make another array, but that defeats the in-place sorting algorithm there.
Okay. I mean, because I vaguely remember when Ben was talking about it in the other class, he said there was a version of it where you could do that.
I would look at that one. But making an X copy is like creating space complexity, which is not constant anymore. But we could take a look at it, at that particular example. Cool? Yes. All right. So at this point, we're currently at 11, correct? So where does 11 go? 11 goes here. Woo, careful. Back up here. 11 goes here, correct? Yes? So let's just write that out again. So we have minus 9. 11, 80, and we have 2. So currently this part of the array is sorted. Where's my current? My current is at 2. My current is at 2, right? So left of current is sorted. Now we want to sort our last element. We take 2, and we put 2 in its current position, in its correct position. So at that point we have minus 9, 2, 11, and 80. So here we have our sorted array. Okay? And the way we'll be using this algorithm, we'll be doing it such that our inner array is looking at our collection in reverse order. Right? In reverse order, meaning I'm looking at my left elements. Right? I'm at position current, I'm not looking forward, I'm looking backward. Okay? All right. So let us continue on here to Xcode and implement this. So create a new file, a new playgrounds. New playgrounds. we'll call it insertion sort. So insertion sort. Runtime, again, worst runtime, big O n squared. Space complexity, what's the space complexity? Constant, because it's in place here. We're not using any additional arrays. Slightly more. Yeah, runtime is the same. Worst case is the same. Slightly more performant than.
So is there, which one is better, this?
Insertion. Here I'll say given a partially sorted array could be a good choice sorting algorithm. Partially sorted and small sized array. Okay? So it has its benefits, right? You have a small partially sorted array, this is good. Optimally, Swift under the hood uses insertion sort given a smaller sized array, right? Swift uses like a hybrid sorting algorithm. Swift's algorithm for sorting is n log n. Uses insertion sort on small partially sorted arrays. I'll put hybrid here. The algorithm is optimized such that it knows which algorithm and how to switch when it does some sorting on our arrays collections in Swift.
I'm just curious, what would be considered a small array?
Like a sized array, like given 100 objects or whatever it is.
Would 1,000 be small?
As opposed to the actual size of it, we don't know that, right? That's like a optimized compiler runtime thing. Right? The compiler will decide what it uses. Yes, exactly. So let's continue on here. We'll have our function. We'll call it insertion sort. Again, function signature is very similar. We have an array. Our function is inout.
Oh, so it has to be partially sorted and small?
If it's using insertion sort, yes. The compiler will know that.
So it has like a number there?
Yeah.
What is,
I'm sorry.
what is considered
Partially
partially sorted?
sorted, like if a partially sorted array, like the numbers is partially sorted, right? So if, when I say partially sorted, this could be an example of partially sorted. So for 5, 7, minus 2.
So this one is not like
The bubble, no. Yeah.
Going along with that question, what would be unsorted entirely?
Like randomized, like kind of like what we had earlier. Because the compiler would know as it's going through it, like is it partially sorted or not.
So it wouldn't work if that was 5, 4, 9, -2.
Yeah.
That would be a compiler optimization question there. I would probably take a look at like internally how does Swift's sorting algorithm works, right? But here we're just trying to expose us to what insertion sort is and what's the runtime of it. I'm giving us some a heads up how does Swift sorting works, right? And at a higher level, this is how it works. As far as like the internals of it, exactly how it works, that's a documentation you'd have to look at.
So,
Like I don't even think that's exposed. Like I don't think that's public. If that makes sense.
so to like kind of clarify that, if this works ideally on small partially sorted arrays,
Mhm.
and Swift's language has a way to determine that.
Uh-huh. Yeah, exactly. Oh, I thought it was, yeah, that's basically where I'm getting at with that there, right? And then at the end of the day, I think it's like a hybrid sort, they're calling it, or intra sort, whatever it is. That's like what they use.
Right.
It's not like they're using merge sort or quick sort. It's like a hybrid of sorting algorithms
Right.
based on the complexity of that array.
And does the one of the potential sources it can
Exactly, that I could go to. It's like a switch, right? Like an automatic shift, kind of, right?
That makes sense.
Yeah. But yes, you could always go deeper into it as far as like how does it work internally, if you want to look at that. And then while we start talking about that here, please bookmark this page. I'll slack it out. Because we'll get to talking about algorithms, but there's much more algorithms, sorting algorithms and all that stuff there exposed to us. And Ray Wunderlich does a great job. This is open source. It's an open source resource of data structures and algorithms, right? So there's algorithms here we're not going to be talking about. There's algorithms here we'll be talking about through the curriculum. But if you want to go further in other algorithms, this is there for us, right? So I'll slack that out. Make sure you bookmark this. Some of the resources we take is directly from here. Like as we go into it, you could take a look at what merge sort looks like. You could review linked list. It's open source. There's different contributors here contributing to it, right? It's a very good resource. So let me slack that out. Cool, great. Let's continue on to our project. Okay, so here we have our insertion sort. Let's continue on. So here we'll say for current, this is what we had. We had a variable called current, which we'll use to go through our array. So for current here, again, we're looking at the first value as opposed to the 0 value earlier in our bubble sort. Array.count. That's the outer array. The inner array, as we said earlier, we want to reverse the inner array to look at the left values. What does that look like? I'll say, we'll call it J for now. For J, we'll say 1 dot. We're taking the full array and we reverse it. Well, not relative. Reverse. So here we reverse what we're looking at. Very similar to what we went through in our pseudocode markup. So now we're looking at the value. We'll have our if block here. We'll say if array, the array I'm looking at, if j is less than array j minus 1. Array j, if we go back to our diagram, where is it? Okay. If we go back to our diagram here, j would represent 9, for example, right? If I'm looking at j, is 80 less? Is j less than 80? That's what we're looking at. Very similar to the bubble sort algorithm. Very similar. So here I'm looking at j. If j is less than j minus 1, then we want to go ahead and swap. If not, different from what we did earlier. If not, we want to break to the outer array, because at that point it's sorted. So if not here, array or left side of array is sorted. Here we want to break, or we could also say continue to outer loop. We could use the break syntax, or we could use continue to outer loop. Remember our labels from Unit 1, right? So here I could say break out of the inner loop, right? Or I could say continue to the outer loop. So that syntax would be the same. So if I say, for example, outer loop here, instead of saying break, same syntax, I want to expose us here. I could say continue to outer loop. Those would be the same, okay? So here, just making sure that we're on board. So basically, let's go back to the diagram. So at this point, if I am looking at this array here, my left array, right? It's sorted already. I want to break and go look at number 2. Right? I no longer want to look at anything. I don't want to look at anything because that's sorted already. Break, go to the next variable. This line? This one reverses. It reverses the collection. So we want to look at backwards. We want to look at the values backwards. So let me go back to the app. We want to look at the values backwards here. So remember, if we had 2 for, oh, that's funny. If we're looking at 2, I want to look at the values backwards in reverse. So I'm looking at 2 here. I want to be able to skip backwards. So I reversed what I'm looking at. I'm not looking forward, I'm looking backwards. So that's why we reversed the collection.
And then we're saying that because the number that it's seeing reversed is what? Less?
If the number we see in reverse is already sorted, then break out of it. If it's not sorted, go ahead and swap it.
Sorted as in, is it if it's greater than the one before it?
Yes, exactly. If not, either we're doing a swap or we're getting out of the loop, of the inner loop. So let's continue on here. So swap, Luba wanted to see what swap looks like, so we'll use swap here. As opposed to what we did before. So before we took care of swap ourselves. Everybody with me? So here we'll use the built-in swap. So swap using built-in swap. So feel free, if you're doing some interview project, feel free to use swap at as opposed to writing the 3 lines. If the interviewer stops you and say, hey, go ahead and not use swap at, then you know how to do it. Everybody with me? Right? Very similar to if you're working with some array and then you could just use that reversed on the array, right? Go ahead and use it until they stop you and tell you, hey, can you do it without doing that reversed or that min or that max? Everybody with me? Know the functions we have available to us. Because I've heard both ways. I've heard where fellows did not use the built-in function right away, and then the interviewer did not give them hints as to, oh, why isn't that person using built-in functions, right? And then they were expecting optimizations right away, right? So everybody's different. So first, I'll just use the built-in function. If they stop me, know what to do manually or whatever. Does that make sense? Okay? All right. So here we'll use swap at to swap the indices. And on our array, swap at, we want to swap j and j minus 1. Again, we're swapping the indices. Those are the indices we're looking at, right? We want to swap those two. And at that point, we swap the values at that position. So if I was looking at, for example, 2 followed by minus 5, I would be swapping those 2 values with that built-in function, swap at. So here we have 1-liner as opposed to 3 lines. Okay. And somebody give me a list we could use.
We have 1, 4, 5, 9, and 2.
We could use a different one. Or we could use this one. It's fine. All right, so we'll use the same one. List 4, 5, 9, and minus 2.
So for this one, we don't have to mark it in out because,
No. They're the same. Remember, they're the same. Where is it? Did I not write it? Stored in place. Space is, I did not. Okay, sorry. So space is constant because sorts in place. Thank you for reminding me. So we have our list. Let's call insertion sort. Again, expecting some sort of reference list here. So we mark it with an ampersand and the list. So now we have a reference. The function, again, this function has a reference to the list array. So it's able to change it in place. So as we change that function, as we change that array internally here, it also changes the outside array. Everybody with me? So at this point, going forward, anytime you get a question in place, automatically no in place means I cannot go ahead and use a new array, manipulate that new array, and return that new array. Right? That's not what the interviewer is looking for. The interviewer is looking for in place, use some sort of reference to that outside object or data structure, and manipulate that data structure. Everybody with me? Cool. So here we have our insertion sort, and we'll just print insertion sort, not insertion sort, list, and print. And here we have -2, 4, 5, and 9. Okay? And no, that's it. That's fine. Cool? Again, the big differences is here we're looking at our collection reversed, and we're breaking out if what we're looking at is currently sorted. We go to the next value by breaking here. Break doesn't break out of my entire function. Break only breaks out of this internal function. Questions? Any questions?
Okay, so this one is faster because the other one is 4 times. This one is 3
It's 3 times, yeah.
Is it because it doesn't have to check it that last time to see that?
We could make the first one a bit more optimized, but at the end of the day, they're both. Insertion sort will always beat bubble sort. But yes, the worst runtimes are the same because we're always looking at worst runtimes. But internally, it could be faster given certain circumstances. All right, so looking ahead, yeah, 1 second. So sorting algorithms, 1 second. Sorting algorithms, we have big O of n squared, sorting algorithms. And we have n log n. So looking at those two, which one is faster?
Insertion?
No. Looking at those two runtimes, which is faster? Big O review. We have quadratic and we have logarithmic. Which one is faster? Logarithmic. Right?
Quadratic is the slopes in general, right?
Not in general, there's factorial, which is,
Factorial is slow.
right? So be careful there, right? We have our big O chart, we have our big O chart bookmarked, right? Anytime you see log n, think it breaks up this problem in two, right? So as we see on Monday, we have like merge sort, it breaks our array in two, it looks at the first half, the second half, breaks it in two, and so forth. At the end of the day, the roast runtime will be n log n, right? Which is way faster than our quadratic sorting algorithms, okay? Everybody with me? Anytime you catch yourself doing a for loop on some array and doing an inner for loop on that same array, stop and think, can I do this better? Okay, because you're approaching quadratic there. Everybody with me? All right, so that's big O review. And that's what we're looking forward to. So sorting algorithms, those are what we saw today. Those are the worst ones. Sorting algorithms. Slower. And I just put faster here. And slower. What we did today, we did bubble sort. And we did insertion sort. And again, we're always looking at runtime, worst runtimes. And here on Monday, we're going to look at merge sort, which is a good one to know. It's very good. and we have quicksort. Eric, sorry, you had a question?
Why do we not have to protect against?
Thank you for reminding me here. Protect against emptiness. We could basically do this here. So we could guard our array count is greater than or equal to 2, else return. Thank you for that. And we'll do the same thing. You could do the same thing for your bubble sort. So here, if it's less than 2, we just want to return. Go ahead.
I was asking about if it was like a repeated digit. So a repeated digit, like what happens when it says 5 to 5? Like does it still just place it in the same place? Or
We could test it. So we'll put a 5 here. Right? Still source it correctly. But importantly, please just put this here for optimization. That optimizes our code, right? Not runtime. It doesn't decrease the runtime, everybody with me? But it prevents us from coming into some list that's only 2 lengths. Right? Everybody with me? Right? Okay, cool.
Should it be greater than 1? Because if you have 2, you can still sort it.
Let's see. Greater than or equal to 2.
Yeah, if it's equal to 2, you can still sort it.
that's correct.
Yeah. So just do greater than 2 here. Greater than 2. It needs to be greater than 2. 1, it will just return that same array.
But if you're doing that's 2, it's equal to 2, right?
If it has 2, I'm sorry?
Because we can sort it with just 2, right?
You could sort it. What do you mean? I'm sorry.
So we're gonna be.
That's saying it has to have at least 3.
I think you had it right the first time.
One second. So array count, we want the array count to be greater than 2 here.
Well, you can sort two.
You could sort 2 elements,
Yeah.
and other than that, we'll just return whatever the count was. So let's just test this. So minus 5 and minus 99. Sort this. Right, we're good here. If we have minus 5, just returns minus 5. If we have an empty set, well, we need to say it's an integer. Doesn't crash, just returns an empty set, right? So here we are good. $100 minus 6, 90 minus 88. Okay? Any other questions so far? Any other questions? Okay, cool. So we're pushing that to GitHub. Make sure you have it there handy. And for assessment purposes, at the end of all our sorting algorithms, what we should know, you want me to scroll up here? At the end of the day, what we should know the runtimes, implementation, space complexities. So looking ahead to Monday, if we have time permitting, we could start taking a look at what merge sort looks like and quick sort looks like. Those are more in-depth algorithms, right? And we'll be using recursion for both of them. So also review what recursion is there, because we'll be using recursion for both of them. All right, so we'll stop here.